objective is to solve a phi equal to q. Okay, A is our coefficient matrix, phi is the solution vector, q is the right hand side. All right. Now, the method of steepest descent is a method that really applies to any linear algebraic system, a phi equal to q. It does not even bother about where the algebraic system came from. In other words, we are not even going to make use of nodes and geometry and all that like we did in the Gauss-Seidel method and the line-by-line method to solve the system of equations, where we actually made use of the physical geometry. We said, okay, we have nodes to the north, nodes to the south. This is what we are going to do to nodes to the north and so forth. Here we are not bothering about that. Okay, we're thinking about it strictly from a mathematical standpoint. Okay, don't care where the equations came from. So what we're saying is, suppose we consider a quadratic function, okay, of the vector phi. So this function, this is a scalar actually, okay. You can see here a times phi is going to give me a vector, okay. That vector times the transpose of another vector is going to give me a scalar, okay, one number. This c is a scalar, of course, it's a constant, okay. Similarly, q transpose, q is your right hand side vector, that times the phi vector is going to give you that's another dot product which is going to give you a scalar. Okay, so this is a scalar function, but it's a multi-dimensional scalar function because phi can be phi 1, phi 2, phi 3, phi 4 and so forth. Okay, so it's a function of n independent variables. All right, everybody got that? So for example, phi could be just x and y, two unknowns. Okay, in that case this will be a two-dimensional function and I can actually plot it. Okay, but if it goes beyond 3 dimensions, I can't even plot it. All right, but I will show you some plots of 2D for you to understand what this function looks like. Okay, so here is a two-dimensional plot. Okay, so if phi is two-dimensional, then f phi looks as follows. That is, if A is a positive definite matrix, then the function is going to look like this. Okay, now here of course this is taken from a book, so they used x1 and x2, but in our case this will be phi 1 and phi 2. Okay, so two axes, and then I'm plotting the function, so it's like a three-dimensional plot. You can also do a contour plot if you want. Okay, and then if the matrix A is negative definite, then this is what it's going to look like. Okay. Another way of looking at it, let me just show you another picture. So this is what I was saying, contour plot now. So you see I have phi 1, phi 2, okay. Oops. So I have phi 1 here, phi 2 here, and these are the contours. You see it might be hard to read from the back, but this contour here says 1, this one says 10, this one says 20. Okay, so really this shape that you have here, it's like a bowl. Okay, or you can think of it as Buckeye Stadium. Okay, all the action is going on here, and then the stadium rises on all sides. Okay, this is what that function looks like, and this is a negative definite, which would be sort of an inverted bowl. Okay, where you can see the maximum value 15 is right here in the middle. All right, and then you have 10, 0, minus 20, and so on. This is minus 200 right there. Okay, so it's like that. Okay, also notice that in this particular case, the example that we were looking at, let me just go back to our positive definite, negative definite. I showed you the contour plots. This is what a two-dimensional function would look like. Okay, but in hyperdimensions, of course, it's difficult to plot, and that's why But the same idea holds, that if it's a positive definite matrix A, then you will have one unique maxima of that function. If it is a negative definite, then you will have a minima of that function. Okay, or the other way around, sorry, minima and maxima. Okay, so therefore what we can say is we can try to determine the minima and maxima of that function by using an optimization procedure. Okay, now how do we do that? we're going to differentiate that function with respect to phi, just like we do in any calculus problem. If we want to find the maxima or minima of a function, we differentiate it, set it equal to 0. Okay, so that's what we're going to do here, except that this is a multidimensional function. So we have to be careful when we differentiate. So f dash phi will have different components, okay, because this is really, if you start thinking about it, this is a function of phi 1, phi 2, up to phi n. Okay, so therefore we have to find partial derivatives with respect to each one of them. Okay, now just again a bit of review of math. If I have a scalar, okay, when I take its derivative, so suppose this is again getting back to geometry. If I have phi, okay, and I do grad phi, this is gradient of phi, that automatically is a vector. Why? Because gradient of phi is d phi dx I plus d phi dy j plus d phi dz k operated on phi, which gives me d phi dx times I plus d phi dy times j plus d phi dz times k. So gradient of a vector, of a scalar, is a vector, okay, because it has three components. This is again geometry I've gone back to, but the same concept applies to linear algebra also, that when you do gradient of a scalar here, okay, phi, then you got to take the components in each of the directions, and when you do that, now this part here basically applied the chain rule. So you can see what it does here is it takes this part and then finds the differential of that, that gives you that, and then it takes the second part, okay, so this is basically chain rule applied twice, and then the last part here, of course, if you differentiate that, you just get q. Okay, now of course this is all done in matrix mode, so sometimes the transpose becomes the regular matrix and the regular matrix becomes the transpose and so on. Okay, but that's the idea. This has been just differentiated using a chain rule, okay, to get that. Now you can see I have half A transpose times phi and then half A times phi. What if my matrix is symmetric? Then I'm going to have A transpose is equal to A. That's my definition of a symmetric matrix. And if that happens, the half and half will combine and I will simply get A phi. Right? I'll get A phi minus Q. All right? So that's the premise with which this method of steepest descent started. The method was originally developed for symmetric positive definite matrices. Okay, positive definite because, or negative definite also it works, but generally for positive definite is what it was developed. It tells us that we have a minima of the function. Okay, symmetric because now we reduce this system to A phi equal to Q, or A phi minus Q. F dash is equal to A phi minus Q. Okay, so what does that mean? That means that if I set now f dash equal to 0, which is what we would do to find the minima of that function, that is the same as solving A phi equal to Q. Because we are saying I'm going to now set that equal to 0 to find my minima. So completely different way of posing the problem. Basically what they're saying here is that instead of thinking of it as solution of a system of linear algebraic equations, why don't we pose it as an optimization problem where we are trying to find the minima of that function f, and that is equivalent to actually solving for A phi equal to Q. Okay. Now, of course, the reason we do that is it helps us understand this whole process of solution much better. Okay, and I'll show you some geometric examples down the road. Any questions so far? Yeah.
This part I didn't understand why the right-hand side, I mean the first expression right-hand side, when you just make a derivative, it yields to this thing. I mean, 1 half A transpose phi plus 1 half A phi.
This one? Yeah, see, you have, if you think about it, when you differentiate A times B, you do A times dB dx plus B times dA dx, right? That's what we are doing here. We are taking the first part and then differentiating this. Differential of that is a 1. Okay, so that's this guy.
It's changed. I mean,
Well, that's because you have to use the relationships between matrix multiplications now. Sometimes the transpose will become the normal matrix and then they will switch positions. Okay, because otherwise you cannot, multiply. All right, but if you write it in scalar form, you will see that that's what it comes out to be. Okay, and then the second part is again, you take this part and you differentiate that part. Okay. Any other questions? All right. So now we are going to utilize this concept to solve A phi equal to Q. Okay. Now our residual vector is of course Q minus A phi. We have already defined that in previous classes. Okay. Now one thing you find here, if you go back to your slide, we said f dash phi is equal to A phi minus Q. So therefore f dash phi is equal to minus R, because R is defined as Q minus A phi. Okay. So that's what I'm saying here, that f dash phi is equal to minus R. So in a gradient-based method, which is what we are looking at here, we approach the minimum and maximum of the function using successive approximations as follows. Okay, so we start with the guess for phi, just like we do in any iterative solver. Okay, and we are going to call that phi with the superscript 0 for 0th iteration, initial guess. Okay, next we have to estimate the value of phi. Okay, and we follow the function along its local gradient or tangent. Okay, this idea is very similar to the Newton's method. I'll show you a picture shortly. So the idea is, if I go back to this figure here, and so suppose I start with an initial guess. I'm just making up something. Suppose I start here. Okay, now the minima of the function is right here. This is my solution. That's where I have to arrive at. What is the value of phi 1 and phi 2 corresponding to that point? That's what I want to find. Okay, I'm trying to solve A phi equal to Q. This is for a 2x2 system of equations. Phi 1 and phi 2, this point is my solution. That's the minima of the function. Okay, I start with some guess here. Okay, now then the question is, how am I going to get to that point? There are many ways to do that, of course, okay, but you have to figure it out algorithmically. So in the method of steepest descent, what it is going to do is, it's going to say, okay, I'm going to calculate the perpendicular at that point. So here's the contour. These are isocontours, okay? So the f dash is basically this vector pointing that way, normal to that contour, okay? Because the gradient vector is always perpendicular to the isocontours, all right? So it's going to move this way. And then it's going to say, if I move that way, how long am I going to go before I stop and change my direction? Okay? So what I'm going to just derive shortly is showing you what it does to actually start moving, and then how it changes directions. Okay? But the easiest way to think of this problem is, again, going back to my analogy of a football stadium. You are up there in D deck, okay? And you want to go down and meet a friend somewhere down there near the field. What is the best way to get there? Okay, now obviously you can't jump over people. Okay, so there are certain paths you can follow, and then you have to kind of figure out, okay, do I go down 3 flights of stairs before I make a left turn, or should I go down 2 flights of stairs, then make a left turn, and then again go down 1 flight of stairs, and so on. Okay, this is an optimal trajectory to doing that. Okay, that's basically what the method of steepest descent is trying to do mathematically for you. Okay. So getting back here, So we start with our initial guess, all right? And we want to get estimate the next value of phi. Okay, what should be my next stop before I change directions? All right. So what it is saying is that my new value here should be the old value, and then I'm going to go a certain distance alpha along the gradient f dash. Okay, I told you, explained that to you graphically, that we're going to follow the perpendicular to that contour and go a certain distance alpha before I change directions. Okay, now of course the f dash is minus of r, so instead of f dash I can use the r vector. All right, so this is basically my update step. This is going to give me my next value of phi. Now the question is, what is this alpha? How much do I go along that perpendicular direction that I started off with before I stop? Okay. Now to find that, what we do is we make the simple argument, again going back to my stadium analogy. Okay, you choose a direction. Let's say you say, okay, I'm going to go northeast to get to my friend. Okay, you start going and you find that you're going down, and then all of a sudden you might find that you're actually going up the stadium instead of, and you see, oh, my friend is there, I just passed him. Okay, so the argument this algorithm is using is, it's saying keep going down because you're looking for the minima, keep going down until the function starts increasing again. Okay, so that's what it's going to do, as you will see in the derivation shortly. So this alpha is determined by saying that, well, along that trajectory that I'm following, I'm going to go to the minima, and because I don't want the function to go up again. In other words, if I'm trying to go down somewhere to the minimum point, okay, it doesn't make sense for me to go up again. Okay, so I'm going to keep going down until that function starts increasing, and that you can calculate by differentiating now with respect to alpha. Okay, so that's what this is doing here, and you can go through the derivation. I'll just go through it briefly. So first thing it's doing is, so to differentiate this, basically we are using the chain rule. We are saying, okay, f is a function of alpha itself, so we do f dash 1 and then d alpha d phi. Okay, because f is not a direct function of alpha, it's a function of phi, and phi is a function of alpha. Okay, this is my phi, which is my function, which is a function of alpha, as you can see. Okay, so if we take that and differentiate that with respect to alpha, we simply get a r naught, which we plug in for this guy, and that's what this expression shows me. Okay, now remember, this guy here, this f dash, is negative of r at 1 at the first iteration. Okay, so ultimately this equation basically gives me r1 transpose times r0 is equal to 0. Okay, now what does that mean? That means that okay, going back to that figure, well, let me just sketch it here. So we had these kind of isocontours like that. Okay, and we started somewhere here and we were going that way. Okay, this vector is my f dash at the 0th iteration, this vector. Okay, which is also equal to, actually the f dash will be pointing that way, the r vector, this guy, which is negative of f, will be pointing that way. So this vector is my r at 0. Okay, this relationship is saying that when I get the new solution, the residual vector at that point will be actually pointing perpendicular to that guy. That's what this is saying. Remember, we said this is like a dot product. Dot product between two vectors is 0. Okay, so r0, which is my residual vector, the very first iteration with the initial guess, will be perpendicular to R1, which will be my residual vector calculated at the second iteration. Okay? And then the next iteration, the same thing will happen. So you will see what happens to the trajectory. Actually, it's a zigzag trajectory. Okay? But I just wanted to point that out. So this is, we know that already, so therefore we get that. And R is Q minus A phi. So we're going to plug that into my expression. Okay? So here is my R1. I've plugged Q minus A phi in there. Okay? And phi 1 is also given by this expression here. So I've plugged that also in. Okay? And did some algebra here. And once you do all that algebra, basically this is what you come up with. An expression for alpha. Okay, now what is that alpha? That alpha tells me from a starting position how much distance should I go before I stop and change my direction. Okay, and it's computed using this relationship. R0 is your initial residual calculated with your initial guess. Okay, A is a matrix that you know, so therefore you can calculate everything in there. Okay, I'll explain the algorithm to you in a moment, and you'll see what really goes on. So you have your alpha, okay, and then once you have your alpha, you update your solution from the old guess. Okay, and so here is the summary of the whole thing. So you start with a guess. Okay, so in this case, K starts with 0. You compute your residual vector. So you initialize your entire phi. Let's say you're solving a partial differential equation. You initialize your entire phi. First thing you do is you calculate your residual. Okay? So you do Q minus A phi. Not, I'll show you how to do that without using matrix operations. All right? So you do Q minus A phi, that gives you your residual. Now you say, okay, next value of phi, next iteration value, how do I calculate that? I first calculate my alpha using this relationship. I have already calculated my residual, so all I'm going to do here is a dot product, okay, and then here it will involve multiplication with A, okay, calculate my alpha. Once I get my alpha, I update my new value. That's my next value of phi, okay, and then I keep repeating the process. And of course I have to check for my L2 norm, which, by the way, this guy here you've already calculated here. So do not repeat that calculation. Just store that value. Okay? So the gradient vector represents the direction of steepest descent locally, and that's why this method is known as the method of steepest descent. What I mean by that is, let me just pop up that image here. Okay, so what I mean by that is that if you take any point on this isocontour, okay, the fastest way to get to the next isocontour is to follow this perpendicular vector, the gradient vector. Okay, if you go any other way, this way or that way, you will reach this next contour later. Okay, because these isocontours are essentially the perpendiculars, vectors are, the isocontours and the perpendiculars, they're of course at right angles to each other, and that's the direction of steepest descent. Okay, any other way it will take you longer. Okay, now of course this changes. So see, by the time I get here, I'm saying, okay, by going this way, I'm going to get to this contour faster. But what about the next contour? If I keep going that way, then that's not going to happen. Okay, now I got to take the perpendicular locally to that guy. That will take me to the next contour fastest. Okay, so that's what's really going on here, and that's why it's known as the method of steepest descent, because you get the steepest rate of descent by traveling along the gradient vector. Okay. All right, let me show you a numerical example now. So 2 by 2 problem. Again, we are doing 2 by 2 because we can plot it. We can see what's going on actually. Okay, so here's my coefficient matrix, and here is my right hand side. Simple system of equations. Okay, and if I actually plot the f function that comes out of this, this is what it looks like. I already kind of showed you in the other plot. Okay, this is the solution right here. So the answer to this system is phi1 is equal to 2 and phi2 is equal to minus 2. That's the solution to that system of equations. Okay, that's right here. That's where we want to arrive, starting from this initial guess of minus 2, minus 2. Okay, what the method of steepest descent is going to do for us, you can immediately see, is we are first going to go along this direction, perpendicular to that contour. Okay, now how do you get that? So you calculate your residual first. We talked about this. So step number 2 is, after you've done your initial guess, step number 2 is calculate your residual. So residual with our initial guess of minus 2 and minus 2 comes out to be that. In 2D, that's like a vector. It has 4 units in the x direction, or sorry, 3 units in the x direction, 2 units in the y direction. Okay, so this is a ratio of 3:2, as you can see. Okay, so that's this vector that I've drawn here. 3 units in x, 2 units in y. Okay, now I calculate my alpha. So that's this operation right here. I'm doing R transpose times R. Here's my R vector. Okay, and then R transpose times A times R. Okay, exactly following the algorithm right like we had in the previous page. And that gives you 0.173. Okay, so what is this saying? This is saying you go a distance of 0.173 times the residual vector along that path before you change directions. And what is that point actually? That's the point when the function starts going up again. In other words, you're going down your stadium. By the time you get to some point, I think I have that in the next slide here. Okay, so you can see I'm going up to that point, which is this calculated value. Okay, and what happens at that point is I'm going down, but all of a sudden now I find myself climbing stairs. So I'm going to stop there because I know my minima is further down, so there's no point going up there. Okay, so now here I stop and I change directions. Okay, this new direction that you calculate, and that's actually shown here. So this is the residual vector first iteration, this is the residual vector second iteration. If you actually do a dot product of those two, you will get 0. Okay, so this is at actually 90 degrees, even though, well, this figure is not to scale, so it doesn't quite look 90 degrees, but that's what it is. Okay, I'll show you a better plot in a moment. And then you go some distance, and then again you switch direction. Okay, go some other distance, switch direction, and so on. Let me show you a better plot of this. Here, this is what happens. Okay, final answer is right here. Oops, sorry. Wait for it to go away. It's right there. -2 and 2. Okay, so you see what it is actually doing, the method of steepest descent. It's taking a zigzag path where each vector is perpendicular to the other one. Okay, and going towards that point. Now you can imagine, I just had the calculations up on the screen a short while ago. What happens with iterations? Here. Okay, you see, this is, I think I've done about 10 iterations, but you see we are still not at the correct answer, even after 10 iterations. Okay? It's 1.9847 and minus 2. Okay? Here is your L2 norm. It's gone down by substantially from 14 to about 0.05, but still not gone down. Now, this is a 2 by 2 problem. Okay, that's something we have to realize. Think about a 1 million by 1 million problem. I mean, how many zigzag paths are you going to take? Okay, it can be a lot of turning back and forth. Okay, and that's one of the problems with the method of steepest descent, that because the search directions, so these are called search directions, okay, because the search directions are always orthogonal to each other, you end up getting way too many changes in directions. Ideally, what we would like is something like this, that from here, okay, once we arrive at this point, we wouldn't like to go perpendicular necessarily, but we would like to point straight at this solution. Okay, we are headed, the first iteration we did head in the right direction, but then, you know, by making the next vector perpendicular, we've kind of shot ourselves in the foot. Okay, so that's part of the problem. So let's see what we have on offer here. So that's what the method of steepest descent does for you. Okay, and generally it takes a lot of iterations. So this is where the conjugate gradient method comes in. Okay, so this method was actually developed by a guy called Lanczos in 1952. Okay, it's considered one of the most, you know, revolutionary works in linear algebra, and, you know, subsequently there have been many improvements to this method, but it's all based on this. All right, so he came up with a simple idea. So he looked at this and he said, well, here is what we are going to do. He said, okay, this is my first search direction. Okay, the next search direction according to the method of steepest gradient is supposed to be this guy. This is the new residual vector, orthogonal. Okay, but I'm not going to do that. What I'm going to do is I'm going to take my old search direction and my new predicted search direction and do a linear combination of that to give me that vector. Okay, now of course, easier said than done. Then you might say, well, what is that linear combination? Okay, if you do a bad linear combination, that vector might point that way. Okay, so that's where, of course, all the mathematical theory goes in. So what he did was he said that instead of making the two search directions in successive iterations perpendicular to each other, I'm going to make them orthogonal. Instead of making them orthogonal, orthogonal to each other. Okay, so R transpose times A times R is equal to 0. That's what he enforced. Okay, and there's a good geometric explanation for why that works, and you know, why that's such an ingenious idea. But we're not going to get into the details there. You know, you are welcome to look up his paper. But this is the basic idea that he worked with. He said that the new search direction should be a linear combination of the old and the predicted new direction, or the residual. Okay, so if you do that, then here is what you get. Okay, now clearly you can see that this is going to give you an improvement just from the graph here. Okay, and here's the algorithm. So I'll just outline the algorithm and then show you an example. So you start with the guess, you compute your residual vector. These two steps are identical to MSD. Okay, and then what you do is you define another vector D, which we will call the search direction. in the first iteration or 0th iteration, you just set it to the residual vector because that's your best option. Later on, you're going to update that in a different way, okay? And then you update your solution using this relationship here, where alpha is given by this, where notice that in the denominator, instead of R transpose times R, we have D transpose times D, okay? Now, very first iteration, D, of course, is equal to R, so therefore alpha, the very first iteration, will be the exact same as what you get for the method of steepest descent. Okay, so that 0.17 that we calculated for that example, that's what you're going to get. So from this point to that point, those 2 points are going to stay identical as the method of steepest descent. It's after that that things start changing. Okay, now how does that change? Well, here is what he does. He calculates the new residual vector. So I have a new solution. Okay, I've calculated my alpha. I have a new solution, so therefore I can calculate a new residual. So suppose you start with k equal to 0, you now have k r of 0 and r at 1. Okay, residual at 0th iteration and first iteration. All right. With that, he calculated a new direction vector. This is what that linear combination was all about. So remember, I had this old direction going that way, okay, which is this guy, d of 0, okay, and my new residual is perpendicular to that, okay, because my old residual was pointing that way, new residual is pointing that way. What this is doing is, it's doing a linear combination of this guy, d at 0 and r at 1, okay, to give me something in between, where beta is just a combination factor. Okay, that combination factor is determined by enforcing that A orthogonality that I talked about. Okay, there's a lot of math that goes into that, but that's what ultimately you end up getting for beta. Okay, so beta simply uses, you can see this is basically the L2 norm square at iteration 1 divided by L2 norm square at iteration 0. Because you're going k and k plus 1, 2 successive iterations. Okay, so that's your beta, and then you execute the algorithm. Okay, so that's basically the steps in the conjugate gradient algorithm. In terms of the number of operations, it's not anything more significant than the method of steepest descent. There is some extra calculation you have to do to calculate this beta, but that's about it. Okay. Number of floating point operations is almost the same. All right. Here is what you get for the convergence of the previous example. Okay, remember we had gone 10 iterations and we had minus 1.98 and minus 2, or plus 1.98 and minus 2. This is what you get with conjugate gradient. Okay, 2 iterations, you get exact solution. Okay, now here is what Langsdorff also did. If you look in his paper, there's a detailed theorem and proof which says that if you solve k equations, k being, let's say, 100 equations, you're going to get the exact solution to this problem in at most 100 iterations. Okay? By exact solution, I mean your residual will go to 0.00000 and so on. Okay, exact solution. Now, on a computer, that doesn't happen usually because it has, floating point or precision errors. But if you did exact mathematics, okay, treat all the rational numbers as rational numbers, work with fractions, okay, this is guaranteed. Now, of course, you might say, well, if I have a system of million equations, I don't want to do million iterations. Okay, true. We don't want exact solutions. We only go up to a certain tolerance and stop anyway. Okay, but this is telling us that, in the worst case scenario, you got to go at most k iterations to get the exact answer. Okay, and which is what you see in this 2x2 example, that in 2 iterations you do actually have the exact answer. Okay, and This is what really it's doing graphically. Again, this is your MSD old, this is your MSD new, and this is what the conjugate gradient predicts as your new search direction, and it takes you right to the answer, second iteration, directly. Okay? Yeah?
Would it be accurate to say that the time per iteration on the gradient method is longer?
Not much. You probably have one multiplication more. Okay? And that's what I was saying, that the number of floating point operations is almost the same. It's hardly any different. Okay? I'll show you a numerical example in a moment. But that's what the conjugate gradient solver does for you. Now, the big downside, of course, is that this is only true for symmetric matrices. Okay? And that's where, when this first came out, it was great, and then people said, oh, but we can't use it for practical problems, because if we have non-uniform mesh, we'll break the symmetry of the matrix. If we include fluid flow, we'll break the symmetry of the matrix. If we have non-uniform transport coefficients, we'll break the symmetry. If we have curvilinear grids, we'll break the symmetry. So what is left? Okay? But of course, that problem got solved down the years too. Someone came up with a method called the conjugate gradient square method, okay, which applies to both symmetric and asymmetric matrices. The foundation, the basic principle is the same of that method, okay. But I'll show you some examples here. We're not going to do the conjugate gradient square in this class, but you will actually do the conjugate gradient method. But let me show you an example of what kind of performance you get. Okay, so here is your MSD. Okay, now I know these curves are difficult to determine, but to distinguish. But this is your. Oops. Keep doing this. So this one here is 161, this is 81, this is 41. Okay? But you see how many iterations it's taking. Huge. Okay, 100,000 plus for 161 by 161. Okay? Pretty expensive. We go to conjugate gradient, and the improvement is really shocking. Here is what you get. Okay, 400 iterations, 600 iterations in this case. Okay, and you see what the residual, this is a log-log plot, okay? So the fact that the residuals are doing this means highly superlinear convergence. Okay, in other words, with successive iterations, these things, the residuals are dropping orders of magnitude, rather than going from 2.1 times 10 to the power 3 to 1.1 10 to the power 3. Okay. So this is what conjugate gradient brings to the table, with very few additional operations compared to method of steepest descent. Now the reason we study method of steepest descent is because it's the foundation of this method. Okay, it's also based on this whole idea of optimization. Okay, finding the minima of a function. But the neat thing about this method is that it it applies or it refines how you do the search, okay, and gives you this kind of convergence. Here is an example I'll show you of. Okay, so here is an example of conjugate gradient square. Okay, just 2 by 2 example again. Notice that now I have an asymmetric matrix. Oops. Doing this here. This guy is asymmetric because you see I have a 2 here and a 1 here. It's not symmetric about the diagonal anymore. In the previous one I had a 1 and a 1. Okay. The solution to this is also -2 -2 or 2 -2. Okay. And just like the conjugate gradient solver, it converges to the exact solution in at most 2 iterations for a 2 by 2 system. Okay. And here is a plot of the residual. This is CGS, conjugate gradient square. Okay. slightly faster than conjugate gradient, but that's kind of, problem dependent. It doesn't always happen. I would say order of magnitude wise, they are similar, CG and CGS. Okay, CGS is, in terms of floating point operations, is slightly more expensive, maybe about 25% more expensive per iteration. Okay, but the performance is just as good as conjugate gradient. Okay, so CGS is what you will find being used a lot in commercial codes. For example, if you're working with a finite element code or CFD code, CGS is one of the solvers you'll see in their list of choices. Okay, now they don't use it just like that. They actually precondition the matrix before using it. So it's usually a preconditioned conjugate gradient solver or square solver. All right, which gives you even better performance. But this is one of the methods that's used quite a lot. Now, one thing you notice here, and as well as in the conjugate gradient plot, is this thing here. Okay, and some people don't like that, because what happens is sometimes when you solve PDEs, and let's say, like if you're solving, let's say, the Navier-Stokes equations, okay, you're going to solve for u velocity, v velocity, w velocity, and then go back and resolve everything. Okay, so you're solving segregated PDEs in a bigger outer loop. Okay, so when you solve the u velocity, you don't want it to get down to this kind of tolerance before you solve the v velocity, because you've got to go back and do this again anyway. Okay, so why get it down to machine accuracy? So what people usually do is they do partial convergence of the equations. So they'd get it down, the residual down to maybe 2 or 3 orders of magnitude, and then move on to the next equation. Okay, and that poses a problem with the conjugate gradient solver, because you can see really from here to here, it hardly took 50 or 60 iterations, even less. I mean, if you really look at it, if I look at this point versus this point, this is a few tens of iterations. Okay, all the work really got done here at the front end, which means that I would still be spending quite a bit of time to go down a couple of orders of magnitude, as opposed to what I would need to go for with 10 orders of magnitude. Okay, so that's part of the reason conjugate gradient solver, some people don't like it. Okay, because the initial rate of descent is very erratic and not very fast sometimes. Okay, any questions? All right.